Okay, today we're going to jump from atoms to molecules, starting to apply the Schrodinger equation and quantum mechanics to what a molecule actually looks like. So now that we're moving from atoms to molecules, a natural question arises, and that is, when do chemical bonds form? And that's really what we're trying to answer today. What is a chemical bond? Why does it form? So let's consider a diatomic molecule. So it makes sense to start perhaps with some simple molecule like AB. And let's think about a plot on an energy scale for molecule AB, where the y-axis here is energy, and the x-axis here is going to be the distance between these two atoms. Right? This AB distance that usually we'll call something like r. Now, if I have molecule and atom A and B really close together, they're basically on top of one another, the energy is really high. If they're really, really far apart, there is no interaction, so the energy is basically asymptoting to what we'll call zero, no interaction. Now, a lot of different things can happen between these 2 points. Maybe it is completely dissociative, and the graph might just be like this. That is, as I move left to right, I'm moving these two atoms apart, the energy is decreasing. No chemical bond will form, this molecule will not be stable. However, most things when they come together form some potential like this. And that is pretty terrible. There should be a bigger dip, a more steep rise, and then this leveling off to about 0 here, so that's better. That is, as I move left to right, over here, B is basically on top of atom A. There's a lot of nuclear repulsion there, and that's unfavorable. Way over here, the distance is very big, like this, and the atoms basically aren't interacting. So the energy is not changing much as I move B even further apart. Right? These two atoms aren't talking to one another. We call that energy at infinite separation 0. So it asymptotes to 0. It increases to infinity as the atoms lie on top of one another. Now, for this will be a bond because there is some stability afforded, and the bond distance, of course, will be this minimum here, where this r then is the average bond length. Okay, so when the energy of AB is a minimum for some finite AB distance, we call that a chemical bond, and the molecule will be stable. Now, electrons we sort of think of as belonging to one atom or another, right? In general chemistry framework, we might think, here's a nucleus, here's a proton, and the electron here, orbits in this classical Bohr model of the atom, and it might look like this. And we know that's wrong now because the electron is not this particle, but this sort of sphere, this cloud of negative charge that is spread out like a wave. But even so, we still assign an electron to an individual atom. Once we bring another molecule in, the picture changes. That electron doesn't really belong to a single atom. That electron in quantum mechanics doesn't belong to atom A, doesn't belong to atom B. It's dispersed throughout the molecule. And there's going to be areas of high electron density and low electron density. There might be higher electron density on A compared to B, but it doesn't mean it's only on A. Right? It's spread out over the entire molecule. There's going to be regions where it's more probable or less probable, right? Or it could be equally probable between the two. Now, what we're really after in quantum mechanics is solving Schrodinger's equation. So, how are we going to do this? In atoms, we have something like this. We've been talking about the Schrodinger equation. The Hamiltonian times our wave function, or operated, I should say, on our wave function, returns energy times our wave function. And these wave functions here, solving Schrodinger's equation, means coming up with the wave functions that satisfy that particular Schrodinger's equation. For an atom, there's a Hamiltonian with kinetic energy and potential energy terms, the potential of which is that Coulomb attraction between the electrons and its nucleus. The wave functions here, the solutions, we've called atomic orbitals. And so those solutions describe then that spatial distribution of electron character around that nucleus. And the energy here of the orbitals is my E term. So there's the wave function that is the atomic orbitals. The energy here is the energy of that particular orbital. Now, in molecules, the equation in the most simple form looks the same, right? It's still the Schrodinger equation, some Hamiltonian operating on the wave function. Of course, here we know this Hamiltonian is going to be different, and that's the real game here, is to solve this new wave function that when I operate with this new Hamiltonian, I return some eigenvalue, which are the energies, times the wave function. And so here we call these wave functions the molecular orbitals. It's still a description of where the electron is, where the probabilities of finding it are in space. Okay, so that's just the notation we're using here. The Hamiltonian now for molecules is what we want to discuss. To figure out where the electrons are in a given molecule, we need to know what are the different forces involved, what are the kinetic energy terms, what are the potential energy terms, and how do we put all that together? Okay, so this is going to be quite long. There's a kinetic energy term first that looks like this, negative h bar squared over 2 times the mass of an electron. And then we're using this notation, this summation, from the first electron up to the n number of electrons. And again, we use this symbol here to denote the kinetic energy terms of the general atomic Schrodinger equation, right? Which has like 1 over r, dr, the spherical coordinates, Hamiltonian for an atom. We're still having that for each electron because there's still a kinetic energy of each electron. Okay, so this is the first term here. We haven't really done anything different for the Hamiltonian of atoms versus molecules yet. This term is just the kinetic energy of the electrons. And we have the notation here to describe all the different electrons, because we're summing up from electron 1 to electron n. The second term here is going to have 2 terms. It's a summation again. But here it's the electron being attracted to 2 different nuclei. So here is where we're going to start to diverge. And the Hamiltonian is going to be different for molecules than it is atoms. Why? Because in a molecule, there's multiple atoms. So each electron is going to be attracted to nucleus A. So this is the distance of electron 1 to nucleus A. The Coulombic form takes a form like this. E is the charge of the electron. Epsilon naught here is permittivity of free space. And Z is the nuclear charge of atom A. Right? This is a molecule here, maybe molecule AB. A and B are different. This is the distance between the electron 1, and atom A. And this is the potential energy of attraction for that electron to the nucleus. There's also going to be the same for electron 2, its distance to nucleus A, its distance for electron 3 to nucleus A, 4, 5, all the way up to the total number of electrons. Now, there's also a nucleus B, right? An atom doesn't have 2 nuclei, only 1, so here, this is different now. And so now this completely is my electron attraction to nucleus A and B. Okay, the A term here on the left, the B term here on the right for nucleus A and nucleus B for a single electron. I'm summing that up now for all the different electrons. Okay, so the Hamiltonian here is not going to have just this one term. It's these 2 terms together for electron 1, but then I have 2 analogous terms for electron 2, 2 more for electron 3, and so on and so forth. right? So electrons in a metal are sort of delocalized. Some of them are core electrons, and some of them are delocalized over the entire surface. So if you were thinking about this like a bulk metal, okay, the electrons being delocalized over the whole metal, that's sort of the situation here on a very tiny scale where we consider the electrons delocalized over both atoms A and B. They can interact with atoms A and B. So there's potential terms here for atom A and atom B. Now we still have more terms to go. The other terms we have are plus. The Hamiltonian is about forces. These negative signs here denote that these are attractive forces or beneficial kinetic energy terms. And the interaction between a nucleus and the negative electron is beneficial, so there's a negative here for each of these summed terms. But now I have a repulsive term, and it's a repulsive term. There's going to be two summations. Why? Because this is a repulsive term between two electrons. And so there's basically two summations here because it's an interaction between two electrons. And it's a Coulomb repulsion. It's the same Coulombic force, so it's the same looking potential. There's no Z term because it's not a nuclei. I don't care about atomic charge. The distance I care about now is between electron I and electron J. Okay, so this is now sort of a double summation, and what this is meant to represent is electron-electron repulsion. Now, if there's only two electrons in the entire molecule, there's just one of these terms. Electron 1 and electron 2. I is 1, J is 2. That's it. There's one term, one repulsion. Right? But now if I have electron 1, electron 2, and electron 3, well, now I have to worry about electron 1 interacting with electron 2, and there's some distance between these two, R1, 2. But I also have to worry about electron 1 to electron 3, R1, 3, and the term from that. And then also electron 2 to 3, R2, 3. So that's all encompassed here with this sort of notation. Right, so this is a notation here. Meaning the distance between electron 1 and nuclei A. And this notation here, the B is probably supposed to be a subscript here, more like this. The radius, the distance between electron 1 and nucleus B. And here it's the distance between electron 1 and electron 2, or electron 2 and electron 3, so on and so forth. Now, we're still not done with the molecular Hamiltonian, if you can believe that. So let's think about what else should there be. Kinetic energy of the electrons, the attraction of those electrons to nucleus A and nucleus B. We've accounted for that. We've accounted for the kinetic energy. We've accounted for all the repulsion between the electrons. What's missing? And what's missing is the repulsion here between the nuclei. The potential energy between nucleus A and nucleus B. Okay, so these terms right here that I'll outline shortly will be all potential. This first one is kinetic, but this last potential one is the nuclear repulsion between nucleus A and nucleus B. There's still E, the elementary charge, but now I have the nuclear charge of A and the nuclear charge of B, because if it's lithium, you have to have a 3. If it's hydrogen, Z is 1. If it's helium, Z is 2. And there's still this Coulombic interaction here, 4 pi epsilon naught, and the distance now between atoms A and B. Okay, so this last term here is the nuclear repulsion. Okay, so in red here is the kinetic term. Everything else is potential terms. there are attractive terms like the first two, and repulsive terms like the second two. And now we have the Hamiltonian here written for a molecule. And it's impressive just to take a moment and think about that we can write an equation, right, with this Hamiltonian plugged into this Schrodinger's equation, which essentially tells us the energy of a molecule. Okay, we can do the same thing for an energy of an atom. So we are starting to literally write down equations that describe the energy of anything. If it's made up of atoms, we can describe it now. Okay, so again, kinetic energy for the first term, electron nuclei attraction in the second term. The last term here is nuclear repulsion, and this one here is an electron repulsion. Again, there's a double summation because I have to start with electron 1 and worry about electron 2 and 3. So I'm holding the first summation for I equals 1 and summing up 1 to 2 and 1 to 3. Then I go back to the first summation and change 1 to 2, and now I'm worried about electron 2, but I'm only worried about other electrons that are greater than I. So if I is 2, I only worry about 2 to 3. And so that avoids double counting. But there's the Hamiltonian for all these different forces at work within a molecule. Now, the unfortunate thing, while it's impressive that we can write down this equation, the unfortunate thing is that it's unsolvable for anything more than one electron. Okay, so we have to undergo some approximations. And the approximations, the most important one, so if more than one electron unfortunately, we must approximate. And here's approximation 1 for today, which is going to be the Born-Oppenheimer approximation. And you may recognize the names of these guys, pretty famous. The first, Max Born, sort of one of the godfathers of quantum mechanics. He's the one that first gave us the fact that, probabilities and observables, right, are based on the square of the wave function, or more exact, the wave function times its complex conjugate. So he was the first one that gave us this probability theory of quantum mechanics. Oppenheimer, of course, worked on actually was the lead of the Manhattan Project, developing the atomic bomb for the United States. So these two guys worked together, and they came up with this theory. Once we started writing the molecular Schrodinger equation, we had to simplify things. And the Hamiltonian really that we wrote back here right, is for a molecule. But there are terms that have to do with electrons, here, here, and here. Draw this one again. And so we could just think about those three terms as being an electronic Hamiltonian. And so what's going to help, actually, is to separate this out and separate my total Hamiltonian for a molecule to be made up of an electronic Hamiltonian plus a nuclear Hamiltonian. So this actually is separable for the following reason. The Born-Oppenheimer approximation goes like this. The electron is so much lighter, I should say, than the proton. It moves much faster. And this is really a classical idea, right? If you think back to this classical picture of the electron orbiting the nucleus, Well, the nucleus is basically fixed, right? And the electron is orbiting really fast. That's a classical picture. It's not right, but it helps us conceptualize the following. The electron is really, really light. It moves around really, really fast. And it's moving so much faster, it's 2,000 times lighter. It's moving so much faster than the proton. The electron density rearranges really quickly. And it does so in such a way that we basically consider the nuclei fixed. So while the electrons are moving and their distances perhaps to the nucleus are changing, the nuclei themselves and the Hamiltonian that represents the nuclear distance between the two A and B atoms, we're going to call that fixed. And so we're going to separate out the electronic term and just solve that. Okay, so this is the Born-Oppenheimer approximation, that you're able to separate out the Hamiltonian of a molecule into an electronic part and a nuclear part. The nuclei are fixed. Okay, so this is the Born-Oppenheimer approximation. The abbreviation for it kind of stinks, I realize, but it is what it is. Okay, so let's see this thing in action. Let's assume first a certain AB distance between my atoms. What are these solutions? So that's what we're doing here. We're going to say there's a fixed nuclear distance that represents a fixed Hamiltonian back here. And think about solving this electronic Hamiltonian wave function. Okay, so I'm really just concerned about operating the first three terms of that Hamiltonian to come up with some energies of the electrons. I'm neglecting this nuclear part of the Hamiltonian down here, so I just have an electronic term. I'll solve this separately and add it in later. That's what the Born-Oppenheimer approximation is all about. Okay, so I'm operating just the three first terms. There's actually more than three because these are summations, but you get the point. These terms in red, I'm operating on a wave function, returning the energies. Okay, and so these are the molecular orbital energies. The total energy, of course, will be these molecular orbital energies plus the nuclear energy. So we'll have to add that in, but in practice, this is what you do. You separate out the electronic and the nuclear terms. You assume a fixed AB distance, and you solve Schrodinger's equation. Meaning you guess a bunch of wave functions, and you figure out what wave function satisfies this equation. And when you do, that molecular orbital energy, you plot on a graph of energy versus the distance between the two atoms. Now you change this AB distance, which will affect this nuclear term, but we're solving it separately. You resolve Schrodinger's equation for the electronic part. Why do you have to resolve it? Because you did move A and B, so the distance from the nuclei to the electrons are going to change as well. Where the electrons want to live is going to change as well. And so I'll have a new wave function that satisfies this new Schrodinger equation, and I'll get a new energy out. And I'll keep doing this for a bunch of different distances between A and B, and I'll plot out what the energies look like. And I'll get some curve like this. And so this is how we actually come up with these curves I drew at the beginning, because you're solving the Schrodinger equation for every different distance between the nuclei. And so you iteratively do this, just solving the electronic part, separately solving and plugging in the nuclear energy, plotting the total energy here as a function of what that distance was. Okay, the nuclear term, remember, is the last term we talked about on the previous slide. ZA, ZB, E squared over 4 pi epsilon naught, the distance between A and B. Okay, but this is constant, right? For this one particular distance. And so Z is constant, E is constant, 4 is constant, pi is constant, epsilon naught is constant. We're holding this fixed. That's what the Born-Oppenheimer approximation lets us do. So the wave function I get out at the end, if this is all constant, well, this times a wave function, if this is all constant, is just that times the wave function. So the energy here of the nuclear term is exactly given by that Hamiltonian operator. Hopefully you can see that. The reason why that's not usually the case is usually we're changing our distance between, say, electron and nucleus. Born-Oppenheimer approximation says I'm going to separate electronic and nuclear. The nuclei are fixed for this given distance RAB, maybe it's here. I know what the nuclear energy is, it's just this for that given distance. But I do have to solve the electronic part, and then I add that to the nuclear part. Together I get this energy. Then I change the distance between the two atoms. I resolve the nuclear term, which is easy. I just update what is the distance, that is the energy. But I have to resolve Schrodinger's equation for the electronic part, add those two together, and plot that energy for that new radius. And I keep doing that to make this graph, and now I know what is the preferred distance between them. It's the minimum energy. Things like to go to minimum energies. Okay, so that'll do it for this first sort of mini lecture where we're talking about the Born-Oppenheimer approximation. We're talking about what the Schrodinger equation looks like for a molecule and where all the terms come from, and why this conceptually represents, as I change the bond distance, what happens to the energies of the whole molecule, and where there is some minimum, that is the ultimate bond distance. Up next, in the next lecture, we'll cover linear combination of atomic orbitals, what these molecular orbitals actually look like, and how we approach solving this Schrodinger's equation by guessing atomic orbitals that might make up this molecular orbital. That'll come up in the next episode. As always, thanks for watching. Feel free to subscribe to this video on YouTube, and feel free to comment with whatever questions you might have about this video. See you next time.